Okay, thanks. Glad to see some more people back again today, and hopefully everybody enjoyed yesterday. So to kick off today, we're getting into a session on AI and climate sustainability. So there's going to be a few different talks in this section that will cover different aspects of sustainability and modeling and AI to do with the environment. So to kick off, first of all, we have a keynote speaker who's going to be presenting kind of a high-level presentation on beyond traditional methods and how to use AI solutions for computational science challenges. So I'd like to hand over now to Professor Ahmed Elsheikh.
Thank you.
Thank you.
Is this working?
You should be good to go.
Okay. So thanks, the speaker, the organizer, for inviting me. My name is Ahmed H. It's a very impressive initiative led by the early career academics or PhD students. I really support these kind of events. I myself was involved in how many years? Almost 20 years ago in similar seminar series, and I understand the challenge of inviting speakers and bringing audience in, especially in weather like this. So thanks to the organizer again for all the efforts in getting this one done. So my name is Ahmed H, and I'm based at Heriot-Watt University in Edinburgh. And today I will be talking about a journey of our work with AI as a group, and not one PhD. Like mostly these two, I will discuss two challenges over multiple PhDs. So I usually kind of like measure it by PhD life, because I don't do research by my hand, or I still do some coding myself, but very little in comparison to what PhD students and PDRA do. They spend significant time working and discovering things, and most of the time things don't work. So it's a very challenging environment. I can't speak about where we end now without speaking on the background. So my background. So I'd have to be here.
Let me just
like
that, and then you should be able to do the right.
Fair enough. So my background is civil engineering. And through civil engineering, I learned to code. At the time, my coding was in MATLAB to solve structural analysis problems. And then I was lucky enough to go after that. I was very interested in dynamics, things moving. So usually civil engineering is static stuff. I was lucky I'm based on Al-Azhar University, which is in Cairo, Egypt. I was lucky to get a scholarship to go and do a master's in Canada, completely different climate. And again, I worked in dynamic stuff, responsive buildings to very strong earthquakes with vertical components. And during my master's, I took a course in finite element methods. I liked numerical methods so much that I got scholarship for a PhD, so I switched my research direction toward learning functional spaces and like doing error estimation for finite element, and took a lot of computer science courses outside my home university at Waterloo University, which is close to McMaster in Ontario. And then I returned back to be an assistant professor at my home university. Didn't work out well because it was mostly teaching. So I was lucky again to secure a PDRA position at Imperial College at the Earth Science Department, where I got exposed to different kind of models, ocean circulation models, mesh adaptivity for these larger scale models. And then through a visit of an academic, I got to work on inverse modeling, parameter estimation when you have observation, very rapid models, rapid modeling techniques for oceans. So we try to do reduced order modeling. And after 2 years at Imperial College, I was so not happy with the lack of sun. So I went to Austin, Texas, at a very renowned institute. It's called now Odin Institute for Computational Science and Engineering. And I worked on this parameter estimation and inverse modeling sampling techniques for computational models. And then after a year and a half, I moved back because I couldn't secure a position at UT Austin. I moved back to Scotland. I'm there for the last 11 years. And COVID made me a runner. So if you want to talk to me about anything outside work, it will be about running injuries. This is last month in North Vancouver, a race there, which was super enjoyable it's not all on mountain biking tracks. There was really challenging hills to climb. But this is me. What about the work? The work is done by an entire group. And even if some of these PhD students and PDRA worked on different topics, machine learning skills are transferable, and the knowledge is somehow is shared between the entire group. So the early ones are in the top here, Xing Shang and Nagore. I will mention them multiple times. They are successful researchers now, Oxford, Drive AI, and the later generations, and the later in the talk, it will be about work of Atish, who is now at Edinburgh University in PDRA on multi-agent modeling. But we worked on machine learning from 2014 from different kind of applications, mostly driven by inverse modeling and data assimilation techniques. But then through nonlinear events, unpredictable work, we got to work on generative modeling for geology. And then we tried to use models based on fitting time-dependent problems, RNNs, or recurrent neural networks. And from there, we moved to reinforcement learning for controlling PDEs. I got funding from surprise funding to work on imaging of the subsurface. So I had 2 PhD students working on image super resolution techniques. And recently, last year, I got a large grant for AI application for carbon capture and storage, which is one of the application I started working on at UT Austin. So, and I have a lot of collaborators working on that. And this is why probably I'm invited here for sustainability, because CCUS is considered to be one of the techniques for mitigating climate change. It's not the optimal solution, but it is one of the tools we have to address that. This is carbon capture from the air or from flutes from the chimneys of factories like cement, and then compressing CO2 and injecting it back to the subsurface deep geological formation, and hopefully it doesn't leak back again. So the outline of my talk is split into 2 parts. Generative modeling. Generative modeling have been receiving significant attention because it have now impact on people's life through ChatGPT and the like. And reinforcement learning, which is, again, I am assuming that a lot of people have heard about AlphaZero and AlphaGo. So this is techniques. And I call them beyond traditional methods because traditional methods, if you come from the computational science and engineering, you either simulate, you have an algorithm which you design, and you argue about the correctness of the algorithms, and you make sure that it converges in a specific way, and it finds one solution only. There is something called uniqueness in the mathematical literature. Or if you come from a machine learning perspective, you train a machine learning model to emulate what you have collected. So you collect a set of training data points, and you try to emulate these as good as possible, and you check its generalization by meaning on a holdout data sets. Generative modeling and reinforcement learning doesn't fall in these 2 classes. And I have to say, when I got to know about generative modeling back in 2016, I was kind of surprised. What is the objective of that? So the first part is generative modeling is how to generate new instance similar to training data. And this is definitely kind of historical view of it. You have images of faces of low resolution, and you want to generate faces. And this is one of the methods or example from scikit-learn, which is the Python machine learning library, which is starter for every master students we work with or PhD students with no background. I kind of point them to start playing with it. And definitely it's now have reached a very, very scary kind of quality. You can generate images. I asked ChatGPT to generate images about University of Glasgow last night. So the campus is beautiful, and we can do that. It will be useful for computer art, for entertainment, for design computer games, or it can be useful for creating misinformation campaign. And now generative modeling is going. We can see trends of it. Can we generate CAD models can we generate, and this will aid the engineering, the process of design of engineering. But most of the effort is generating art. Why? Because most of the data we have is collected through the internet. When we started this, we asked it, okay, there is something called GAN. Buzz about it, can we use it for generating geology? Before that, we can talk about what is geology. Geology is a description of the subsurface underground. The subsurface could have reservoirs, which could be, we can use it for extracting water. We could use it for injecting CO2 back. I call it back because we extracted CO2 in some forms over the last 100 years. So we have these layering systems, and geologists spend significant time to try to understand the geology of the subsurface. They can look to what's called outcrops. They can collect well data. When they dig wells, they collect samples, but they can't have a complete image of the subsurface. They can have an image, you call it seismic images, but it is very low resolution based on sending pressure waves and collecting reflections and reconstruction of the subsurface, but the quality of these images are very low. And if you want to use the subsurface, you need to acknowledge the uncertainties, that there is no truth. Unless you really dig something, you don't know what's in the subsurface, far away from where you dig. Things can change. And there is a field of research to deal with that problem, which is called, it's never been called generative modeling, but it is a generative modeling field. It's called geostatistical field. That if we want to generate multiple realization, which satisfies that this blue in this edge here and blue in that edge here, and probably that there is red in the middle, but in between, we want to have variability. This variability we created artificially based on, for those who work with Gaussian process regression, based on what's correlation lengths. And that idea of generating multiple realizations or multiple instances of the data conditioned based on what we observe is very, very similar to collecting faces and then say, can we generate a new face? But in the geology, we were successful, or the academic community was very successful in modeling systems which are smooth. Usually they call it like sand depositions. Once there is a channels, they developed algorithms, but these algorithms were not good. So they developed these, what we call it, multi-point geostatistical algorithms, where they somehow collect patterns of an idealized geology and try to generate conditional on what we have seen. If we have seen these three blue or four blue, what will be the probability of the rest of the pixels? And they do it sequentially. And they managed to make it work to generate geological realizations, which looks real, which have these patterns of deltas and, but always these algorithms grow in complexity and we're disconnected from what we observe. What we observe is either outcrops or satellite images, because satellite images gives us images of rivers and deltas, and these are usually buried in the underground. So if you give it million year, what the deltas of today will be buried underground. So the existence are underground. So the challenge is, these algorithms are good, but they are not perfect. Can we improve them by generative modeling? And we need to stress on, we are not interested in simulating one phase or simulating one geology. We are interested in simulating multiple realization of the geology to understand uncertainties. What do we use this geological realization for is that we couple it afterwards with fluid simulation, which describes the use of the subsurface. And then we can assess, make decisions, we can optimize the system, we can make predictions. Is the system safe or not safe? Whether that will be a decontamination problem for the subsurface, where we try to clean prior contamination, whether it is injection of CO2 down in the subsurface, and then when you inject things, there will be pressure buildups and things might crack, and we don't want to do that. So we don't want to trigger seismic events. The other application where generative modeling have found itself is in weather prediction, because it's inherently uncertain problem. So if we collect realization of the weather over the last few days, can we generate in the future 6 hours, 12 hours ahead? Or we can use these generative artificial worlds to train agents to emulate human intelligence, or for stress testing of systems. So I'm assuming that there is maybe few of you, maybe 20% of the people who are in this room have seen what's generative modeling, but this part here is for those who haven't seen generative modeling. The very easy concept of generative modeling is to collect these samples we have seen, the sample of faces, and try to build somehow the general pattern, an average of all the faces. This is the first pattern. We call this basis function. The second is a second basis function. So we call it, we collect the samples and try to get a vector of principal components. And then if we want to generate a new face, we sample from these basis functions. We sample n random variables, and then we multiply the mean. We leave it multiplied by 1, and then the first function which somehow describes the variability is multiplied by 1 random variables. The second random variables, these basis functions will be embedded in this matrix as the columns, and Z are the random weights, and B is the bias or the mean. The idea of when we apply this idea to systems which have these sharp features like channels or edges, we end up with realizations which are smear. If we can transfer this to be, instead of a linear operation, this is a linear operation only, to a big nonlinear operation, then we are starting to think of generative models using neural network, where this function here, which takes a random sample from an easy to sample distributions, normal random variables, we pass it through a very nonlinear function, and then we get a face, or we get a geological realization. How do we design this big G? We put a big neural network, because everything we do now is replace an algorithm with a neural network. But the challenge here is that neural network is very difficult to train. So, and this neural network is counterintuitive for people who don't work on generative modeling. We are used to neural network where we feed an image from the right-hand side, and we get a probability of 100 classes. This is a classification problem. Is it a dog? Is it a cat? Is it a horse? Is it a house? This neural network is operating in the opposite direction. We input here a vector of 100 random samples generated from an easy to sample distribution, either a random variable from zero mean, normal random variable from zero mean and 1 standard deviation. And then through a set of transformations, and this you could think of these cubes as a matrix vector multiplication, and then we apply nonlinearity on top of it. It's not as simple as that. It is a matrix with specific sparsity patterns and repetition inside of it, and it's called convolutional operation. And before the nonlinearity, we have normalization layers and more details. But then we aim that once we have the weights, an oracle gives us a perfect set of weights. We sample, and then we pass the input through a set of transformation. We get an image. We hope that this perfect, somehow oracle-given weights will be a good neural network to get images of different breeds of dogs, for example, or images of different realization from our targeted geology. How do we search that space and find the weights which corresponds to that? By the way, we are talking about hundreds of millions of weights to find. That's almost an impossible task. And usually, if you train any neural network, you need to guide that neural network by saying to it, what is the loss function are we doing well or are we doing bad? And this is how do you drive your improvement or adjusting the weights. We don't have an analytical loss function for an image which is good or bad. Is the image we obtain is geology or non-geology. So we delegate that task to another neural network, which is a neural network which is standard in supervised learning, which takes an image and generates 0 or 1. Is it a geology or non-geology? Is it good dog or just pure noise? That's an easy to train in neural network. So now the loss function, which is a standard loss function, have been delegated to this neural network, which we can train. The question is, if you train this to say geology versus non-geology, and you train it very, very well, and you go back to use it as in the loss function of training this neural network, that is like anything you do, it will give you zero loss function. The search space is so large here of the weights that most likely you will get an image which are so bad. So it's like a teacher saying to the student, this is bad. This is bad result. This is bad result, without giving them direction to improve, because it's always 0. You are producing 0. You are producing 0. The weights needs to be updated by giving a direction. So the whole idea of GAN is not to have a very mean teacher, by meaning a teacher which always gives you 0, is to not to train the teacher very well, to make the teacher make mistakes himself, to say, and not to give 0 100%. It's just to train it a little bit that it says, this is more dog-like versus more noise-like. And that somehow untrained teacher gives a direction for improvement for the student. And then you keep iterations, the students improving and the teacher improves. So they both grow together in the skill, and many cases, both of the training fails and you don't succeed, but under conditions, you can solve this min-max problem successfully. So let me iterate again. The first step is that this is the teacher. Teacher takes images and says, is it real or fake? And that teacher we can train very easily because we have training samples, which looks like geology. And we can generate these random samples, which are definitely does not look like geology. By having the generator with random weights, it will generate noise. So we can train the weights of the teacher, or what we call discriminator, a little bit by giving it 100 samples of the geology and 100 samples which are generated by this generator. And we can update the weights here a bit. And then the next step, we say adjust the weight of the student or the generator such that it can fool the teacher. In the start, the teacher will give it 0, 0, 0. We try to say, okay, adjust the weight such that if we pass the information from these through the generator, we got these images. The teacher, because it's not a very trained teacher, says, oh, this is good. This is not non-zero, like, or approaching 1. And you iterate between the two. And this idea was published in 2014 by Ian Goodfellow. Some people dispute that this method have been proposed earlier, but it was shown to work and provided somehow templates for it for people to use in 2014. We started working on this, and it started to find its application in geology in 2017. And multiple group from Imperial College, Sheng Shang at that time, my former PhD student, and a group at the University of Lausanne in Switzerland. But these groups here dealt with a problem which is already solvable, by meaning they targeted the generation of the geology, which is this kind of geology. We targeted the geology which is really hard to design an algorithm for, and we didn't use standard GAN at that time. We used a variation of GANs, which are called Weierstein GAN. The learning of these GANs are mostly unstable, or was mostly unstable. there was some ways to train it. When you train a neural network, you need sometimes to, if you have limited training data, you need to regularize it. If you have maximum amount of data like YouTube or from the net, regularization becomes less important. So here, there was a technique to regularize that training and stabilize the training, and we utilize it, and this was called Wasserstein GAN. After the success of these three groups, there was an industrial interest. Now, once we have industrial interest, we try to solve problem for the industry, and they fund projects through universities. So we started working now by using industrial funding to start to adopt what was somehow, it was accelerating too fast. There was every 2 or 3 months, there is a new paper on a new version of GANs with improved training. This is from 2017 to 2022. We were trying to catch up at that time. We are on the receiving end of all of these massive big groups. We are talking about Sheng first, one PhD student working in my group in this sense, and then in 2018 or 2019, I hired another PhD student, Al Hassan, to work on this, and he was experimenting, but then every time new variations with new state of the art on generating faces appear in the literature. So we couldn't catch up with that, and I think after 2022, we stopped. I didn't get funding more for that. Definitely all of that superseded by diffusion models. In terms of quality in image generation, this is what's used by ChatGPT or DAL-E or all the commercial offering now. But we were interested now in solving a problem for people who deal with geology. The people who deal with geology, they don't have an internet of images. They have people who are usually drawing their perception of what's underground. They have databases of outcrops, which is images of these vertical cuts. If you go to the Grand Canyon or actually you go on the North Shore, North Sea shore here, there's a lot of outcrops around there. And the industry started to talk to us and say, okay, we are interested in questioning these systems. Will it be able to train on some limited data we have? Will it generalize? And the second saying, will it work with one non-stationary data? And I will explain what's non-stationary data. So this is funded by our industry, by the geology is mostly a Total company or Total Energies. They are interested in understanding their subsurface reservoir, whether they use it for sustainable use or as they envision now to use it for CCS or non-sustainable use. But I worked with geologists to design how can we test if GAN can generalize beyond its training data. And we designed some data sets where the color yellow is 25% of the entire image. And these are channels versus background. Or 30% of the area is covered by channels, or 35% covered by channels, and the rest is the background. So now we know that we have samples here, 100 sample of this, where the different channels, 100 sample of 30%, 100 sample of 35%. So now we have designed a test case where we know that our data set does not contain the in-between and does not contain below than 25%. And now can we train again to generate on 20% or 27% channel proportion? And now can we argue that GANs can do that? So we explore with what's called conditional GAN. Conditional GAN is used usually for conditioning the image generation based on a vector, to say to ChatGPT or DAL-E, you generate a dog. So you need to encode the dog in a number, and then after that, so it's a mapping from natural language processing to a number, and then you generate the image. We showed that these conditional GANs can generate with some tricks, and we call it tricks because we needed to change the training algorithms a little bit, can generate valid in between classes. And we even can generate beyond the classes. So we are extrapolating now, but you can't expect it to extrapolate far ahead. So we can generate a proportion which is 10% if our training data is from 0.25 to 0.35. We can generate very high proportion because the channel merges in non-geological patterns. We learned that we need to specific kind of conditional GANs are better than others. We needed to stress during the training to generate these unseen conditions to feed it to the training while we work. But we say, okay, we understand if we work with limited training data, how do we train GANs to work beyond our training data? We said, let's take it to the next step, where the condition is local, where some part of the images are covered by thick channels and some part of the image are covered by thin channels. So this is low proportion here, and here is high proportion. And we designed our training data to be only from left side here. So we have a grid of 4 by 4 of conditional proportion, which are somehow fed to our generator, high to low, and then we flipped it, high to low from the other side. So our training data is like this only, spatial condition. We never have any other instance of training data beyond this kind of pattern. And after training, we can generate patterns which never existed in our training data. So we put 0 here and 0 here, and we feed this condition, and we want to generate multiple realizations satisfying this condition. So we have a diagonal channel. We have a channel up here and down here. So now we are using GANs to somehow with an interpretable conditions and with some stochasticity to generate multiple realization. This was the first in our field. This was very similar to people who provide segmented image and then generate an image on top of it with texture. So it's not like unique in the terms of computer science, but it was unique in terms of geology. And then we targeted the direct learning from data. The first starting point, we criticized the algorithm, which was designed by humans, that it injects so many assumptions in it and lacks satisfaction of data. So we collected the satellite image, or there was satellite image online from Southeast Asia, for Brahmaputra River, which is a very interesting river and long and shows a lot of patterns. We got a segmented image of it. We get the skeleton of the river. We collected small patches of that. We rotated it to be aligned such that the direction of the river is dominant from bottom to top. We needed somehow to coach the training data to be easy. We don't want to confuse the generator with rotations in the same time as we are confusing it with many other things. And then we apply on it these spatially conditional GAN to generate patterns which are satisfied by this proportional conditions, and then multiple realization of it. The question after that, how do we use that? If I am able to input a specific pattern here, which is conditions, and I have still the 100 knobs of random noise to generate the different realization, and I'm applying this in inverse method later on, I have too many parameters to solve. I need somehow to assign a prior on these, and the noise doesn't have a prior. It is so we worked with a group in Norway which have more experience in that, and we saw that this image can actually be inferred from these low resolution subsurface imaging, which we call seismic. And we can first calibrate that from specific sources of data. And then later on, we try to pinpoint subset of these random realization using another source of data. So this is our journey with GANs. It surprisingly started while I was playing with the Kaggle competition. in 2016 or 2015. At that time, somebody posted, can we generate more training data using GANs? And then I started reading, what is GANs? I didn't miss it from the literature myself. And then I said, okay, Cheng, you're my star PhD students, go and read this. And he read that, and it fails. And then he came across Waziristan GAN, and then published a paper about it. But the goal here was to replace a generation algorithm with a lot of details injected by human by big deep neural network, replace analytical function of good and bad with a learned another neural network. The advantage is that once we generate this neural network, it's very fast to generate realizations and no hidden assumption about the data. But the disadvantages are many. The training is slow and could fail. Needs a lot of expertise with GAN. My understanding, we didn't work with diffusion models. The diffusion models might need an order of magnitude more of data, but maybe is more stable. But for all algorithms, the validation of the trained model is almost near impossible. Do you guarantee, there is a guarantee that this deep neural network, which replaced our algorithm, is valid, is always generate something? Can I put it in a loop where everything is automated and I trust it that it always will generate to me what I wanted it to generate? That's a very hard question to answer. The second part is reinforcement learning. Reinforcement learning, I'm assuming those who work in early machine learning saw the buzz of Google acquiring deep learning and said, okay, we can use these techniques. We can, it's very impressive. Let's use it for multiple applications. And at that time, I had another star PhD student. His name is Nagor Kani, and he was working on emulation of dynamical systems, which changes in time. And I asked him to investigate reinforcement learning, and his experience at that time that these algorithms fail very easily. And this is true for anybody who works in newer algorithms. So GAN early on was failing more than succeeding. And reinforcement learning in 2014 or 2015, 16, where you try to train things, they would fail. And still till now, they fail more likely. So his experience was not positive. I managed to succeed to obtain funding for another PhD student. His name is Atish Dixit, who's now at the University of Edinburgh in the multi-agent learning group as a PDRA, to work on subsurface control using reinforcement learning. He succeeded. He published 2 or 3 good papers on that topic. But then during COVID, I applied for funding to apply the same techniques, subsurface or Navier-Stokes flow. Subsurface flow is somehow slow, and the uncertainties of the medium underground is very high. So it lends itself to specific kind of equations and specific kind of difficulties. Navier-Stokes flow is flow around bodies. It's usually fast flow. It have different kind of mathematical structure. The question is, can we generate or build the efficient reinforcement learning to do control for 2 classes of problem? And this is a canonical problem for active flow control, where we have fluids moving around the cylinder from the left to the right. And after a specific speed, oscillations start to happen and what's called vortex shedding. One way, this vortex shedding corresponds to is a drag force, which is the force pushing the cylinder towards the flow direction. Oscillate here, if you look to here, oscillate around 3.2 value up and down because of this vortex shedding. And the lift force oscillate around 0, which is somehow is lift up and down. There is significant amount of effort to dampen the effect of this vortex shedding using different active techniques. One of them is to have what's called zero mass jets, where we inject fluids from the bottom to the top or from the top to the bottom, but with equal quantities. So we have just a pump which sucks from one side to the other side. The question is, what is the magnitude of this jet along the time? We want to design an algorithm which somehow collect observations using pressure probes in the fluid field and take actions directly. And this flow control problem is a nonlinear flow control problem. Classical algorithms for control works very well for linear problem, but really hard for nonlinear problem. Again, a problem where machine learning can help because classical solutions are somehow do not exist or very hard under very limited condition, very limited. You need to set a lot of conditions to make it work. So it operates under very limited or strict conditions. Reinforcement learning works in games, works now in superhuman performance in chess and Go, and somehow people are trying hard now to make it work for robotics because we don't need to prepare our training data. Reinforcement learning, for those who don't know, reinforcement learning is a joint optimization and data acquisition and supervised learning, by meaning that we are exploring the space. What is the best action to take if you observe this observation? So you are searching for the best action, and you are doing action sequential in time. And in the same time, you are exploring a surrogate function, which are like modeling, like using like any regression function. And you are narrowing the domain. Again, if you are solving active learning problem where you collect your own data and then build a surrogate function and then you optimize it, you are faced with this with dilemma between, do I do exploration a lot and slow the learning, or do I exploit so much and maybe end up in local minimum? And that's only for one time frame. If you are doing sequential, then the problem is Markov decision process, extremely hard to solve. Techniques for solving it using dynamic trees exists, but again, it's very, very expensive. So our aim is to exploit this reinforcement learning for controlling of an environment, and this is a physical environment. It's not a computer game. It is a simulation which takes a lot of time, or an experiment which we can't repeat a lot. So if it is fluid simulation, we don't have the experiment access to the experiment, or if it is a simulator using OpenFOAM simulator, it's a C++ big code to solve and takes hours to simulate. So we don't want this interaction between the agent by taking action and the environment, collecting new observation, and somehow this R reward, are we doing well or bad? Are we reducing the drag or are we increasing the drag? Are we achieving our objective or not? We need a lot of these, and usually it's in terms of millions. So our first challenge was to generalize now. We were dealing with the subsurface simulator. The subsurface simulator was, or Atish was dealing with that, written in Python. Our algorithm which we evaluate is written in PyTorch. Everything can work together seemingly. Now we want to generalize to different classes of problems: CFD solver, solid mechanics solver, particle solver. We will not gonna rewrite everything in Python or write PyBind interface for it. So one day I came across this precise library, which is a library to couple solver. If you are solving fluid dynamics problem and the fluids are pushing a structure like a wind turbine, you can have the wind turbine solid structure solved in DEAL or calculus, and then you do the interface data exchange between the two through the time stepping through precise library. And the idea is to plug in the controller as an extra solver. And I had one smart PDRA who helped develop this library. His name is Musaib Shams, and we published that. He's now a postdoc or maybe a research fellow at Imperial College. And we developed this very clear and clean interface to interface deep learning or reinforcement learning algorithms with simulation packages. And because this library is super useful, we started by looking to subsurface flow in the underground and Navier-Stokes equations. We started to look to problems beyond our design, which is fluid structure interaction as well, which is like modeling of really challenging engineering problems which have impact on sustainability and renewable energy generation. I didn't touch, or I don't think I have time to touch on the learning algorithms for reinforcement learning. There is two network in the flavor of the algorithms we are using here. An algorithm which predicts the future value of the actions we take. It's similar to in chess. If I take this movement, what is the value of the board? Am I good to succeed till the end of the game? And there is a network which observes the entire state or the observations we have, if it's partially observable, and take action. Do you inject this way or that way, and what's the magnitude of injection? The good starting point is spinning up openai.com. This is a good tutorial, but this is one of the stable algorithms which we start with always to evaluate, but it's not very fast. We validated that. This is a published test case, so we wanted to validate can we work on fluid mechanics problems and do the control for it under standard conditions, and was coupled with very applied and well-tested simulation package called OpenFOAM, and we succeeded in the learning. One cautious word here: reinforcement learning algorithm learns to cheat. So we need to really alleviate the cheating by regularizing what we call the reward. If we are only objective is to minimize the drag, we need first to average the drag oscillates here up and down. So we need a clear signal by averaging it over some set of cycles. So it is uniform. It doesn't learn or doesn't get a confusing signal. Is it going down because we are going on the descent part of the cycle? So we average it, and the average will be more stable. And we want to regularize by limiting the lift, because we don't want huge forces coming up and down, like huge magnitudes of injection. But this regularization have been observed in the literature as well. Now we have a library to do things which nobody have tried before. We have a cylinder which is moving in the, like now we mounted it on a spring. So now we have fluid structure interaction problem, where we have a cylinder which is we are allowed to move and change the mesh around it. And we interacted with a second solver for the spring. And we now, because the precise library allowed us to interact between the solid solver and the fluid solver, and we plugged the third solver, which is our controller, and we managed to control that problem. There's some equations here which are messed up, and we can dampen these by controlling the force. And again, we don't design the controller. The controller is learned based on pressure observation around the cylinder, and based on that, it takes best action. We extended further to have a solid flap, and if the fluid itself goes back and forth. And the question is, if we mount jets on the solid flap, can we control that problem? I think this is one of the I don't think that people have controlled fluid-induced deformation problems before using reinforcement learning. And we managed to minimize the deformation. For that, we are taking that to some of the industrial partners to study how can we dampen deformations around floating wind turbine. It's a problem will be extremely challenging, because we will have the waves. We will have two-phase flow. First, you have the air, the water, the open surface, and then you have the solid itself and the deformation of the solid itself. So this was one extension. Minhui, who is a very smart PhD student in my group now, is working on accelerating the learning itself by embedding a small model inside of the reinforcement learning algorithms and modifying what's called model-based reinforcement learning. And he managed to get 10x learning for specific set of problems, not for all problems. We need to be very careful on not overselling what we are doing. If the model is very hard to approximate, because it's nonlinear model, then it guides wrong policy. But when the modeling errors are small, we can succeed in accelerating the learning. So there is other pieces of the puzzle we worked on, which we try to emulate physical world. Instead of solving partial differential equations, to emulate it using data. But after many trials, I reached this conclusion that numerical simulators set the bar very high. We cannot emulate physical systems if it is an idealized system. If you want to spread heat inside of a plate or emulate a structure to design this table or a building, these are numerical simulators provide very good solutions. But if you want to calibrate physical models where there is some unknowns, like weather forecast systems, then you have a problem because the modeling errors are large. And this is an area where I had one PhD student worked on. I am hoping to raise more funding to get that. So when we try to solve numerical simulators, there is model errors or simplifications, which is observed as a modeling error. Modeling errors can be emulated using machine learning models. This is one of the directions we experimented with. We can only say that numerical simulator, we can emulate them when they are super expensive. But then you reach this dilemma. You created something fast but wrong, or you don't know when it fails. One of the attempts, one of the people mentioned in this image is of the people in my group, Marcus, who is working now on specifically some parts of the numerical solver are extremely expensive. He's plugging that part or replacing that part by machine learning part. So we are injecting CO2 in the underground, and then CO2 is acidic. For some formation, geological formation, there is a chemical reaction happens there. If you want to simulate that, it happens a process at very different speeds than the fluid movement, and it's extremely slows the simulation by 100 times to just do that. So that part, we are replacing it with machine learning. And maybe the optimizers we are using for training neural network emulators are not built for these stiff systems in the numerics. But we had good success in emulations for when we are aiming for uncertainty quantification, where we are aiming in understanding distributions. Why? Because one model will underestimate and the second model will overestimate. But again, the conclusion I reach is limited to the scope of the problems which I tested. I don't generalize that. But control, if we find a policy using a search algorithm, we can always go and test it in the best simulator we have. So this is a good and worthy endeavor to do control and optimization assisted with AI and machine learning. Novel scenarios are beyond AI, and unless there is no alternative, I wouldn't promote for that. Current projects, one of the biggest projects, very hard to manage is on CO2 capture and storage, where we work on the whole process. We said in our proposal to UKRI, there is a lot of literature on capturing CO2 from the chimneys of cement factories. But the tools which is used to capture is called solvent, it bonds with CO2, and then we need to debond it and release CO2 and concentrate CO2, and then use the chemical product again to capture the next batch of CO2. That process is energy intensive. Can we design a material, which is a solvent, which is more efficient? This is one of the parts where we use machine learning to discover solvent. Along the line, there's many other groups are working on material discovery pipeline. And we ended up having like estimation of properties, and then we can validate it with very expensive simulator later on. But then the search space of molecules is very discrete. You change chain, and then you end up with different properties completely. So we are very struggling with that part, but with some successes. We are doing so once we got CO2, we need to inject it in the underground. We need to control how do we inject it with the uncertainties. This is reinforcement learning. We are having this simulator, Marcus work on making the geochemistry part or the chemical reaction faster. And we have a part on the policy analyzing of literature and patent, because a technology like CO2 capture and storage doesn't live on its own. It lives within a technology, with other technology. People will not going to spend that much money on CO2 capture and storage if there is an alternative solutions which are more efficient and less costly. So we need to understand the trajectories of technologies evolution. So we do some natural language processing and clustering of patterns. So this is the third team. We are now to the advertisement part. No, not yet. One of the pressing part is I'm finding now is communication of results. We have this generative model. We can combine it with reinforcement learning or a controller. I go to companies and they are definitely do not understand what I'm talking about. So we are somehow trying to work on integrating the web interface with the loop, and you're going to find a lot of people talking about that under the name of digital twins, but I think I overrun my time. Now the advertising part, I have a research fellow position open on reinforcement learning till the 8th of September. If you are interested, come and talk to me. We started an AI for net zero webinar, definitely much newer than your current initiatives. We started this last summer. We are, when I say we here, it is the 7 funded project under this AI for net zero initiative by UKRI, covering almost all universities or most of the universities in the UK. We are starting by talks from these 7 funded projects. My project and CCS is one of them. But from next month, we are opening up the webinar series to all the researchers who are working at the interface of AI and sustainability. We alternate between senior researcher talks 1 week, and then the following week, 2 speakers, early career academics. So we are looking for speakers, so contact me if you are interested in participating. And we need to acknowledge the funding. A lot of funding for the GAN's work was funded by Total. All the reinforcement learning work is and beyond is funded by UKRI. And thank you.
Well, thank you for a very comprehensive and interesting keynote talk to start off this session. We are running a little bit late because we started late, but I think we have time for maybe 1 or 2 questions if anybody has anything they'd like to ask. Yes, certainly.
Yeah, thank you for that. You mentioned the numerical solvers are hard to compete with. And in the same slide, you have a remark that if you have time-dependent machine learning tools, errors accumulate. So my point would be, in numerical analysis, a numerical solver is only as good in some sense as the analysis permits. Otherwise, you just have to believe that it's true. So in some sense, error control through analysis is key for the confidence one has in numerical solvers. So in the machine learning side, is there a rather attempts to quantify error in the same way that you would in numerical?
So machine learning is a very experimental technique. The analysis of it is very poorly understood. You have many, many knobs to tweak, and you don't know when it fails. So up to my understanding, everybody who tried to do analysis on machine learning emulators started to simplify the systems so much that it becomes one layer of neural network with very simplified nonlinearity in it. So they can perform the analysis, and it works in very simple classes of equations.
So you're suggesting there's a big area for exploration there.
For exploration, which can be analysis of machine learning models and error propagations in these in time.
So if I could, the second question, since I know we're short of time. So you're referring to systems with different time scales, and then equivalently you talk about stiff dynamical systems, so in the same spirit, multiple scale.
Yeah.
So what is the kind of the state of understanding when faced or confronted with a problem, which you recognize is spatiotemporally multiple scale, multiple space scale, multiple time scale? The methodology in applied math would be one of using asymptotics. So matched asymptotics is the philosophy where you break the problem up into, if you like, partitioning space and time in appropriate ways, and also seek to capture the condensation of dimension onto low-dimensional manifolds, where solutions in some sense are empirically or maybe numerically identified as living. What's the analog in this machine learning world where you live?
So I was lucky to experiment with multiple, with this over multiple years. So some problems have the multi-scale in space only. So think of fluid around grains, but we are studying kilometer scale. You would ask yourself, is the flow around every grain matters if you are studying something at kilometer scales? And there was a literature on that, on developing multi-scale time-independent problems. And our experience with it is that aggregating average properties is a learnable process. But solving the large-scale problem, you would never be able to emulate it because you will have combinatorial collection of sources and boundary condition. You can't collect training samples enough to do that. So we published some work on saying that aggregating the small scale problems is learnable, and then you feed it to a coarse scale solver to solve somehow steady state problem, because the local problems are somehow will have some repetition in it in the training data.
Just to use a word then, so the phrase I would use for that is homogenization.
Yeah, so homogenization, exactly. So we can do homogenization in that. We tried to do homogenization, and then we succeeded in that, and we published it within one method or heuristic for homogenization for applied engineers called multi-scale finite volume, which is getting basis functions. We said that learning these basis functions are good, and actually learning these basis functions allows us to have a machine learning models which we can know when it makes a mistake. So these basic functions have to have some properties like the sum to one partition of unities. When we try to predict the basis function, it doesn't sum to that. We know that we are data deficient. We are extrapolating now. We need to do something. But then when we tried to do that with time, we failed miserably. We failed miserably. Like we tried to publish with these techniques, which is based on LSTM, and we published some results, but in terms of robustness, these methods are not robust. And for those who play with ChatGPT-like systems, at one time, I think 3 or 4 months ago, there was a way to ask ChatGPT to take its output and produce something again, to take its output and produce something again, and then it starts to hallucinate completely and produce its training data. For the same reason, if we try to predict the next state based on our predicted states, it is this error feedback. We had an attempt for many small systems, very, very small system, and I used to present that machine learning models operate usually in an explicit form, by meaning it just predicts the next time step, predicts and then takes the input to the next time steps. We might need these to emulate numerical method where we control the error. So we go and keep feeding it like fixed point iteration. But again, it was an experiment on a very simple Burger equation, and it showed that we can solve the problem. When we tried to extend it to other problems, it failed. We keep seeing impressive results about the people who are doing weather forecasts, but the weather forecast system lends itself to a lot of complexities that the numerical solvers are not able to handle. So this is a gap. So it was very interesting to see Google, I think last month, trying to put the machine learning inside of a solver, not the opposite way, generate solver, and then this is an interesting discussion. But I think that one day we will need to have a reliable, after all of these easy wins with machine learning, we will need to sit down and say why it works, how robust it is, when it fails, but this community and I think this is maybe historical as well. People developed things before they fully understood and analyze it and learn it from the mistakes. But the mistakes here will be huge if we deploy things on large scale. It might be collective failure. It's not like what we have. We have few instances of experiments. Everybody will fail in the same time, and that's definitely there is systematic risks in AI, and it's completely under perceived. It's huge for people who know the risk of it. But very good questions. I'm happy to discuss first. Yeah.
Okay, thank you. I think with that, we should probably go and get some tea and coffee, but if you have further questions, then I'm sure...
I'm here all day.
Perfect. So just a quick reminder as well, we have the poster competition. So if you haven't voted yet, then please do. If you have voted already, please don't. And then we'll be meeting back again in, let's aim for 5 to 12. So we'll stay a little bit behind schedule, but we can pick that up through lunch. Okay, thanks.